Hello, welcome to this video. This is 2-1. We are going to dive into the world of derivatives, essential idea and foundational concept in calculus. We're going to explore what instantaneous rate of change is in this video and connect it to our previous understanding of, I would say, one of the favorite topics in math, which is average rate of change. Definitely an essential concept in AP pre-calculus, okay? So that is what we are learning today. And we're going to jump off talking about the average rate of change. What is the average rate of change of a function f of x over an interval a to b? Well, you may know as average rate of change as slope, also known as rise over run, also known as delta y over delta x, the change in your outputs divided by the change of your inputs. These are all good. And the essential one that I feel like is engraved into my brain, y2 minus y1 over x2 minus x1. For calculus, we are going to want to use function notation, have this idea, especially given a function. Average rate of change is f of b, or f of your x2, your second x value, minus f of a, the function value at your first x value, divided by b minus a. So all of these say the same exact thing. It's our change in our outputs divided by our change in our inputs. But what does average rate of change tell us? Well, it tells us the average increase or decrease of the function. So whatever you're talking about, if this was talking about how much money is in a bank account, or the height of a tree, or the position of a particle moving, that's what you're talking about, the average change or increase or decrease of that function over an interval. It's very very important. I guess, hold on, let me say here, per unit of x, it's always a rate over an interval. So average rate of change is cool. It tells us the average change, but it's not the end-all be-all. We'll get into that in a second, right? So how do I calculate average rate of change? We generally see average rate of change in three situations. I guess four if you count like a story or a word problem, so you contextualize it. But we often see it with a function. So right here is a function given in analytical form or algebraic form. The f of x equals the square root of 2x plus 3. They say here, what is the average rate of change over the interval? -1 to 3. How do I calculate that average rate of change? Well, we need our y values, so I have to find what are the function values, right? Because my average rate of change, and I can start off here, average rate of change is going to be f of 3 minus f of -1 over 3 minus -1. Watch out for when you're subtracting a negative. Make sure you always use parentheses there, so you end up knowing that it's addition. Well, I need these values. I need to know what is f of 3. So we're going to plug it into that function. Square root of 2 times 3 plus 3. That gives us 9. So we have an output of 3. So f of 3 is 3. And then I need to know what is f of -1. So I do the same thing. I just plug in -1 into my function and we compute. Looks like -2 plus 3 gives us 1. So the square root of 1 is 1. Okay. And now we can go ahead and we can just plug these in. So f of 3, that is 3. I'll replace that. And then we have here f of -1 is 1. So it looks like our average rate of change is 3 minus 1 over 3 plus 1, giving us 2/4. 2/4. Now, we can reduce that, but in AP Calculus, you do not have to reduce that. You can leave it as long as it's numerical. So where could I stop, Schwarberg? I don't want to have to do all that. Well, you can stop as soon as it's numerical right here. Once you have numbers, once it's numerical, you can stop. If it's an FRQ question, if it's multiple choice, you're going to have to find that 1/2. Let's look at the next form. The next form that you often see average rate of change given is in a graph. So here I have a graph and my interval -1 to 3. Here's -1. Here is 3. And I need the average rate of change over that interval. So what I'm going to go ahead and do is I'm going to do the same exact process. I know that average rate of change is, assuming this is called f, f of 3 minus f of -1 over 3 minus -1. So what are these function values? So f of -1. I like graphs and tables. I feel like they're really easy because you can find the function values. You don't have to do some computations. You can just visually see them, assuming they're nice numbers. Here at -1, it looks like that y value is 0. And then for 3, f of 3, it looks like that y value is 8. So 3, my y value is 8. Okay. And we replace. So f of 3, that's 8, minus f of -1, that's 0, over 3 minus -1, which ends up being, again, 3 plus 1. So here we have 8/4, which we all know is 2. That's average rate of change. Sound familiar? Good. The other one that we're missing is a table. We'll do a table here in a second. All right? So average rate of change, and I visually want to go ahead and connect this too. So our average rate of change is 2 over this interval for this graph. So I'm going to go ahead and make a linear straight line dashed through these 2 points right here. And this is what we call, in mathematics, we call it a secant line. It's a line that goes through 2 points. The average rate of change will be the slope of that line. So on average, you can see per unit of x, we grow 2, right? I go over 1, I go up 2. I only connect it to average rate of change. I rise 2, I run 1. I rise 2, I run 1. So that's the average rate of change. Well, what about if I don't care about that whole interval? What if I want to know what happens from -1 to 0? Is my function increasing 2 right here on this interval? Oh no, I'm going down. So maybe average rate of change isn't always the best idea. What about this concept called instantaneous rate of change? What if I made that interval smaller and smaller and smaller? This would be called instantaneous rate of change. The instantaneous rate of change of a function at x equals c. C is some x value, some point, is defined as, again, it's still the slope, but it's the slope of not a secant line. We call it a tangent line, And I'll show you what a tangent line here is in a moment. But it's very important that you know that the instantaneous rate of change is at a very specific point. So it's the slope of the tangent line at a given x value, whatever one you want. This is a big idea in calculus. We call it a derivative. A derivative. There's the big idea. Derivative, instantaneous rate of change. Maybe write this right here. Derivative equals, not AROC, we call it IROC. Instantaneous rate of change. And we need some notation. In mathematics, we love notation for this. So a derivative has this notation, f prime of x. This is f prime of x, okay? So if there's a number in there, that's the instantaneous rate of change at that specific point. So I want to give you guys some visual of instantaneous rate of change. There's a curve here, and I can do my best to draw some sketch lines, but I'm going to use my friend Desmos. We're the best of pals. Here's a function, and I want to show you the instantaneous rate of change at a very specific point. So here, this orange dot is the specific point in question. You can see, we'll connect it over here. Here's this a value. I'm going to drag this. So we'll make our x value here, it's called a. We'll make it 0. So notice, there's my point. My x value is at 0. So what's my instantaneous rate of change? Well, notice it's going down, right? This dot is starting to go down. So that would be a negative slope, and you'll see that quantity right here in the m round. So m for slope, it's -1. So at this point, do I decrease 1 and run 1? Yes, I do, right? And so this instantaneous rate of change, I can drag it. And so at a specific point, do you see how it's changing? This rate of change now at this point, right? I didn't even go over 1. Now I'm here at 0.7, and that slope is -2.33. So I want you to just keep your eye on this m round right here, how this average rate of change changes, or this instantaneous rate of change changes as I drag this this x value. Now, the black line that you are seeing, that is a tangent line. This is a tangent line. And a tangent line is a line that touches a function at one specific point. So notice it only touches at this one x value. Yes, over here I know it eventually intersects, but it's only going to touch at one specific point in the area. So you can see how it only touches at that one x value, okay? So that is what we call a tangent line. Have you ever heard someone say, sorry, I went off on a tangent. I was teaching this math lesson, and then all of a sudden I thought about playing badminton with my daughter, and then so they went off on a tangent. Something made them think about that, and then whoop, they're gone. You know, their original course is gone, and now they're off on this trajectory. Going off on a tangent, it's calculus connected. Isn't that cool? That's what instantaneous rate of change is, the slope of the tangent line. All right, so let's go ahead and explain the meaning. Let's interpret this derivative right here. It says explain the meaning of f prime of 3. F prime of 3, that's how you would enunciate this and read this in English, this mathematical notation, is equal to -7. So what does this mean? This means that the instantaneous rate of change at x equals 3. Very, very important that you understand that this is at x equals 3. Is -7. That's what that means. Okay? So the slope of the tangent line at x equals 3 is -7. Okay? Pretty straightforward. So, we're not always given a derivative, and sometimes we have to go ahead and use function values to approximate or estimate that derivative. So we're going to talk about that now and how we do that. Reminder, the derivative of a function tells us the slope of the tangent line to the curve at that point. And sometimes we're not able to find that exact derivative. In these cases, we will estimate or approximate the derivative using a very important set of words here, difference quotient. And actually, I'm going to use different colors here so I can kind of highlight something here. Difference quotient. So this is important in AP calculus, and I believe in AP pre-calculus 2, we talked about this. So hopefully you've had that experience, and that will help. But what we want to do, if we want to approximate a derivative, f prime of x is approximately equal to the average rate of change, and we want to use a difference quotient. So what is a difference quotient? Well, you're going to have difference, which in mathematics means subtraction, over, and here quotient in mathematics means division. So I have to have difference, so two differences, and a quotient. Okay, so f of b minus f of a over b minus a. I had a brilliant student said, hey, I know what the values are. Can I just go ahead and jump straight to the values? Do I have to put f of 3 minus f of negative 1 over 3 minus negative 1. And my answer was yes and no. I guess you don't have to, put that exactly, but you better put the function values, like the actual numbers. If I scroll back up here, you better at least show this in AP Calculus. There's a question on a tabular FRQ where they ask this question and they want a difference quotient in order to earn the points. So you have to show a minus. And actually, I don't like this. This is a red flag here. It's a plus. I want to show a difference quotient. So I really, really, really want the minus. I guess up here, you could jump to 8 minus 0, and you would be fine. So numerical, you're done. And you show the difference quotient. But always show a difference over a difference. Okay? That's what a difference quotient is. Very important. Okay, so how will the AP exam ask us to do this? They'll usually give you, three kind of scenarios here. They'll give you a table of values. This is the most common, and this will show up on a FRQ. We'll look at an example here in a second. And what you're going to do here is you are going to use 2 points. And a difference quotient. They may give you a graph of f of x, and what you're going to have to do is you're going to have to calculate the slope of the tangent line. Or, similar to the table of values, use 2 points and a difference quotient. Now, if they give you an equation of f of x and you have a calculator, you're going to use the derivative function on the calculator, and we'll explore that later on in this unit. Use the derivative function. Of a calculator. Really easy with Desmos. You literally just type in f prime at that value after you define the function, and it gives you the derivative. So Desmos Chat app is pretty awesome with that. Okay, so let's go ahead and see how this is applied on the AP exam. Here they say the function f of x is continuous and differentiable. Ooh, new vocabulary word possibly for you. For all x with selected values given above. First of all, differentiable just means that you can take a derivative at that point. Okay, so we'll kind of ignore that. We'll come back to that vocabulary word. But this should give you some PTSD from the last unit. You should be thinking, hey, this reminds me of IVT. And that's good because this FRQ usually asks to approximate the derivative using average rate of change, and it will ask you an IVT question. So it's good that you're linking those. But here they say approximate f prime of 2. So here's the x value they want you to approximate. F prime of 2 is approximately, and we do this with average rate of change. Now, I want you to look at the table and notice 2 is missing, but ask yourself, where would 2 live? Well, 2 would live right between 1 and 3. So I'm going to use those x values. This is going to be my A, this is going to be my B, and I'm going to use average rate of change to approximate the derivative, the instantaneous rate of change at 2. So this is going to be f of 3 minus f of 1 over 3 minus 1. And I love this table of values. Are so awesome because I don't have to compute. The y value at 3 is 1. The y value at 1 is negative 2. I'm going to use parentheses because it has a negative. I'm not going to mess up. And in the denominator, again, 3 minus 1. So here's your difference quotient on the AP exam. That's numerical. You are done. You have earned the point. But I'm going to turn the tables on you. I'm going to say this is a multiple choice question. What's the answer? And then you're going to do 1 minus negative 2. Well, that's 1 plus 2 gives us 3. Denominator, 3 minus 1. That's 2. 3 over 2. Okay? Fractions are numbers too, okay, people? You don't have to go to a decimal, so 3/2. We're cool with it. I want you to pause me. I want you to try B right here. What is f prime of 5? Try this one and I'll show you the answer here. All right, here is how you estimate f prime of 5. Let's start with good habits here. Did you guys write f prime of 5? And then 2, I'm going to challenge myself right here. I use the equal symbol. We're estimating or we're approximating here. So really, I want to use some tilde symbols there. I want to use the approximation symbol. This is approximately this average rate of change. F of 7 minus f of 3, because 5 is going to land right in between here. And the AP exam will always give you something that is, equidistant between these two x values. So don't worry about that. But anyway, you should have gotten 4 over 4, which is 1. You could have stopped. You could have stopped here at 5 minus 1 over 7 minus 3. That would earn the point as well. Okay, so hopefully you got that. All right, tables, my favorite, nice and easy. Let's go to graphs, my least favorite. Not always super nice and easy. Okay, so we're going to use a graph to approximate the following values. G prime of -2. This is the instantaneous rate of change at -2, or the slope of the tangent line at -2. So what I like to do with these is I like to go ahead and I like to place a point at that x value here, which is -2, and then I'm going to draw a line, okay, that will estimate this. So I'm going to draw this tangent line right here. And what I'm trying to do is I'm trying to generate some points that I can approximate g prime of -2. So g prime of -2, I'm going to use a difference quotient here. And these points, since I approximate, I really like to just make a set of points, and then I'm going to plug this in here. So I chose this point and this point because they're nice y values. Choose nice y's or nice x's to make your life a little easy. So I have here, I guess my first point has an output of -1, and my second output is a +1, and then I have to estimate these x values, okay? And again, it's just an estimation. Don't rack your brain, to 3 digits what this point is. Here I have a -2, so if I go this way, it's going to be let's say -2.2. And then for my second point, I'm going this way, so that's going to be more positive, so -1.8. -1.8. Okay, and so this average rate of change, okay, y2, so 1 minus -1 over -1.8 minus -2.2. And we end up getting 2 over -1.8 plus a 2.2 gives us a 0.4. If I multiply all these by 10, we get 20 over 4, which is much easier to know that that is approximately 5. Approximately 5. Okay? Instantaneous rate of change. Pretty cool. Let's look at another one. I'm going to go ahead and I'm going to skip B, actually. B's up here. But let's look at C. I'm going to look at C. Here is G of 1. So where's 1? It's right here. Here's 1. This is my x value. And I want to make a tangent line for this point. Okay, so do my best here to draw a tangent line. Woo! That's a bad tangent line. So draw this tangent line. We'll go there. Okay. So I'm going to use these 2 points, maybe this point and this point here, to calculate that. Let's see, is that concave up? Okay. And so those 2 points, let's go ahead and say, I don't know, 0.7, 1, and 1.3, -1. So then my average rate of change, so g prime of 1 is approximately here, -1 minus 1 over 1.3 minus 0.7. which gives us negative 2 over 0.6. If you wanted to use that trick multiplying by 10, we get negative 20 over 6, which is approximately negative 3.6-ish. No, negative 3.3. It's a 2, not a 4. Negative 3.3. Okay? So I want you to pause the video. I want you to try this. We are near the end. I want you to try it for D, which is g prime of 0. G prime of 0, which is this point right here. And I want you to look at this. Is this point going to, what's the slope going to be compared to this one? Is it going to be bigger, smaller? How's that question? Go ahead, pause me now, try that one. Okay, hopefully you tried that one. Here is approximately what I got. I got a negative 2.5 slope. I used the points negative 0.2, 4, 0.2, 3, and that gave me negative 2.5. A little bit more positive than the one before, the negative 3.3. This is more steep, right, in a negative direction. So this is actually a greater slope. Don't freak out about like the lack of black and white answer on this, because the key word here is approximating. So it's not going to be exact, and the AP Calculus exam is not going to ask you to do this with a graph. So this exercise might be a little futile, but we're just showing you how you can approximate with a graph. Now, what would actual applications be? Well, the AP Calculus exam loves to ask you about horizontal asymptotes, horizontal tangent lines. And horizontal tangent lines is when you have a tangent line that is horizontal. It is completely flat. Now, these horizontal tangent lines, very important, and we'll explore them more. They happen at extrema, at maxes and at mins. So you often see this portrayed in a couple of ways. They'll just flat out ask you, where is the horizontal tangent line? Or they'll say something like this: where is g prime of x equal to 0? Where is the instantaneous rate of change 0? So imagine throwing a ball up in the air, right? And then right at the top, when the ball's increasing, right before it starts to decrease and fall, it pauses for a split second, right? That's where the instantaneous rate of change is 0. That's going to happen at the extrema. So here I can say this happens at x equals negative 0.8, and it also happens at 2.1. This is going to happen at extrema, maxes, and mins. This is also known as a horizontal tangent line. Maybe you want to write this here too. Horizontal tangent line. So with graphs, what are the applications? What are the applications? Well, and this is where we'll end here. They love to have us put these tangent lines or these instantaneous rates of change in order. So they give us questions like this: put the following in order from least to greatest. Let me erase this graph so we can go ahead and see these. But they'll usually give you a positive slope, a negative slope, and a 0 slope. So g prime of 0. Where is g prime of 0? Well, that's right here. This slope looks negative to me. I'm going to put a negative underneath it. G prime of negative 2. Where is that? Well, that's over here. That looks positive to me, pretty steep. And then G prime of 2. Where is that? Well, that's right here. Negative, but it's almost 0. Almost 0. So if I was to put these in order, instantaneous rate of change from least to greatest, we have G prime of 0 is less than G prime of 2, which is less than G prime of negative 2. So that's what they love to do. And we can use this same exact exercise. Again, they give us some of the same values. I know at 0 it's negative, and I know at 2 it's close to 0. But what about at 1? What about at 1? I have a new one here. Here's 1. Well, that's negative. But which one would be more negative? I think we already explained this, that g of 1 is more negative. G prime of 1. That was like negative 3.3, which is less than g prime of 0. And then in this case, our 0 slope is the biggest one. So go ahead, pause me. I want you guys to try C here. So try C on your own. All right, and then here is the solution to this one. This one had a curveball, which is a very good curveball. Is g of 1 is a point. It's a point. I know that the slope at 1 is negative, but they want the point, the function value. The function value is 0. So that's going to be your lowest. G prime of -1. This should be a negative, right? Whoop, -1 right here. -1. That is right here. It's positive. It's close to 0. And then we have g prime of 3, which is, woo, very steep. There you go. Okay, in this video, did you learn what instantaneous rate of change is? Hopefully you did. It's the derivative. It's the slope of the tangent line. That is it. All right, go ahead, give me a thumbs up, like the video. I'll see you in the next one. Take care.